Today we're going to talk about thermochemistry. Thermochemistry is studying the heat of reactions. And so the first few slides are just vocabulary. I would like you to copy the vocabulary, fill in the little handout worksheet that goes along. I did upload that on Google Classroom as well. And so make sure you know the vocabulary that goes along with this section. The video will focus more on the math than the vocabulary that you can get from the equation. So I'm going to scan on through the vocabulary. And so I'm going to stop here and talk about heat. Heat is a measurement of energy, and the unit that we use to measure heat is in the joules, and that is our International System unit. The older system is known as a calorie, and we still use calories in the United States, but we use something called kilocalories. They don't tell us a kilocalorie, they just write it as a capital C. So the older system again is calories, and one little c calorie is 4.184 joules. And I would like you to memorize that, 4.184 joules, always goes with the J. And I do apologize, I do have a little slight cold. 1 kilocalorie, also known as a capital C calorie, is 1,000 calories. And so when you see on your food packages 100 calorie pack, that actually is 100 kilocalorie. They just write it as a capital C calorie, we won't think of it as kilocalories, but it really is kilocalories. And I would like you to know that in 1 kilojoule there are 1,000 joules. So our first problem is just going to be a simple little conversion. If you had an average sized baked potato and it had the energy value of 686,000 joules, how many capital C calories, which are known as kilocalories, would you have? So it's just a simple little converting. And you would put it over 1. Your joules would go down, and you would convert to the lowercase calories first. 1 will go with the lowercase calories, 4.184 will go with the joules, and that will cancel. And then you'll bring the small lowercase calorie down, and the capital calorie, if you prefer to write kilocalorie, that will be fine. In 1 kilocalorie there are 1,000 calories, and so those will cancel. And if you multiply and divide and round for sig digs, you will see this is 164 big C calories, so you could write it as big C calories, or you could write it as a kilocalorie. So 164 calories in a baked potato. And again, that's what we see on our food label. They find this out by using calorimeter, where they actually burn food, and that's how they figure out how many calories of energy it has. Next is known as specific heat. That is a vocabulary word I would like you to know. It will be on your quiz. It's the amount of energy needed to raise 1 gram of a substance 1 degree Celsius or Kelvin. And I also would like you to memorize the specific heat of water. It should look familiar because it's the same as the conversion to a joule to a calorie. So water's specific heat is 4.184, and this is its unit, joules per gram Celsius, and that little circle goes with the Celsius. And these are being multiplied here. So this is the unit for this. If you'll notice, these are some other common things. You don't need to know those. But water takes lots of energy to heat it. That's why it takes water so long to boil. Gold, on the other hand, would heat it really fast. It doesn't mean it's going to melt. It's just going to get hot really fast, and it would also cool down really fast as well. This is the formula that we're going to be dealing with. Q equals mCp times delta T. What the letters stand for. Q is the heat, and it's going to be measured, it's either lost or gained, going to be measured in joules. M is mass, it's going to be measured in grams. Cp is specific heat, and it's going to have that weird unit, joules per gram Celsius or joules per gram Kelvin. And then delta T is something new. Unless you've had physics, you probably haven't seen the delta. Delta means change in. And the way you find delta, you take the final temperature and you subtract the initial temperature, which means the beginning temperature. That's how we find delta T. So we're going to do 2 problems. One's really easy and one's a little bit more challenging. The first one says, how much heat is lost when a solid aluminum ingot, which just means a bar of aluminum, has a mass of 4,110 grams, cools from 660 degrees Celsius to 25 degrees Celsius. And so it's going to lose its energy to the environment. The specific heat of aluminum is 0.902 joules per gram Celsius. So the formula we use is Q equals mass times specific heat times the change in temperature. And our mass is 4,110 grams, and that is of aluminum. The specific heat, which is what Cp is 0.902 joules per gram Celsius. And then the change in temperature, it's always the final, which would be 25, minus the initial, which is 660, which is a difference of a negative 635. So if you want to just replace that with negative 635, that would work. You simply multiply, and then we're going to round for sig digs. You get a negative 2.35 times 10 to the 6th power. And you can see grams will cancel, and Celsius will cancel, and that will leave you with joules. And so what this is, excuse me, is the amount of heat lost. It's losing heat, so that's why it's coming out to be negative. Since it says how much heat is lost, you don't necessarily have to put the negative, because the negative is kind of understood in that situation. So pretty easy formula. If you wanted to use that formula in a triangle, you could use it even though it has more than 3 variables. Q would go on top, the mass, the Cp, and the delta T would go on bottom. So it would look like that. Again, this is going to be heat measured in joules. This is going to be your change in temperature. And again, that could be Celsius or Kelvin. Because it's the change in, it will be the same no matter if it's Celsius or Kelvin. So you don't need to convert ever. This is going to be specific heat. And this is going to be mass. This one's measured in grams. This one's measured in joules per gram Celsius or joules per gram Kelvin. And it doesn't matter if it's Celsius or Kelvin. We're just not going to use Fahrenheit. So the last example is going to require a little bit more detail to it. You've got a piece of metal, it's really hot, it's at 100 degrees, and you're dropping it into a container of water. So the metal is going to lose its energy, and the water is going to pick up the energy. And it's going to be the same amount of energy that's going to be lost and gained. Because of that, we could set the Q of the iron equal to the Q of the water, which is the heat. Because this is losing energy, this would be negative. Since this is gaining energy, this would be positive. Another way to put that would be, and we got to again make the left side negative, we could replace that Q with the mass times the Cp times the delta T of the iron would equal the positive mass of the water times the Cp of the water times the delta T of the water. And now we can plug numbers in. We're going to make sure we remember the negative. The mass of the iron was 21.5 grams of iron. The specific heat of iron is 0.449 joules per gram Celsius. And your change in temperature, well, I don't know the final temperature. I know the initial temperature, and I know the initial temperature of the water, but I don't know the final temperature, but they are going to reach the same final temperature. So I'm going to let it be X. And the first one will be X minus 100, because that's the iron. Everything over here is about the iron. And over on the other side, everything's about the water. We'd have 132 grams, which would be the same thing as 132 milliliters, because however many milliliters you have of water, that's how many grams of water you would have, because the density of water is 1 gram per milliliter. So some of the problems on the worksheet will give your water in milliliters. You just need to know that's the same thing as grams when you weigh it for water because of the density of water. And the specific heat of water is 1.814 joules per gram Celsius. And then I don't know the final temperature, but it is going to be the same as the other side, which is X, and I know the initial temperature. So now I can do this algebraically. I can multiply those together and distribute, multiply those together and distribute, and add like terms. Or you can go into your calculator and you can use the y equals. You can put this side in y equals 1, and you can put this side in y equals 2, and you can graph them, finding the intersect. If you can't see the graph, you can zoom fit, and then if you still can't see the graph, you can zoom out, and you zoom out several times. Once you see the graph, you can hit your second trace button and go down to intersect and find the intersect. And when you find the intersect, and unfortunately I can't show the calculator on here because the two programs don't like each other, but if you need help with your calculator, again, you're going to put this in y equals 1 and this in y equals 2, and then graph and find the intersect. The answer to this one, which is going to be our x, it comes out to be 21.37, some other numbers. We would round that to 21.4 degrees Celsius. So if you need help with the y-intercept, please let me know. And that's all of the specific heat problems, with this one being the most challenging. So please come see me if you need some help.